I'm Daze Thomas, Assistant Professor, Department of Artificial Intelligence and Data Science from SNS College of Engineering. Today, let us discuss about file system implementation. We have system calls at API level, but how do we implement these functions? You can implement these functions on disk or in memory structures. We have a boot control block which contains all the information needed by system to boot operating system from that volume. It is needed if volume contains an operating system, usually the first block of volume. Then we have a volume control block, that is a super block master file table, contains the volume details like total number of blocks, total number of free blocks, total block size, free block pointers or array. Directory structure organizes the files like name of the file, inode numbers, master file tables, etc. Then we have a file control block which contains many details about the file, the inode numbers, the permissions, the size, dates, etc. NFTS stores into master file table using a relational database structures. File permissions, file date, file owner, file size. These are the different data that will be saved in a file control block. Then in-memory file system structures. We have a mount table storing file system mounts, mount points, file system types. The following figure illustrates the necessary file system structures provided by the operating system. This is the diagram for in-memory file system structures. First figure refers to an opening file and second one refers to a reading file. Okay, how to open a file, how to read a file. Then buffer holds data blocks from secondary storage. Open returns a file handle for subsequent use. Data from read eventually copied to specified user process memory address. Then we learn about partitions and mounting. Partitions can be a volume containing a file system, that is a or a row, just a sequence of blocks with no file system. Boot block can point to boot volume or boot loader set of blocks that contains enough code to know how to load the kernel from the file system, or a boot management program for multi-OS booting. We have root partition contains the OS. Other partitions can hold other OSs, other file systems, or that is row. Mounted at the boot time. Root partition is mounted at the boot time. Other partitions can mount automatically or manually. At mount time, the file system consequency checked, is all metadata correct or not? If not, we'll fix it and try again. If yes, add to mount table and allow the access. Then we have virtual file systems. Virtual file systems on Unix provide an object-oriented way of implementing file systems. Virtual file systems allows the same system call interface to be used for different types of file systems. This separates file system generic operations from implementation details. Implementation can be one of many file system types or network file system. Implements vnodes which hold I in nodes or network file details. Then dispatches operation to appropriate file system implementation routines. And this is the diagram for virtual file system. And the API is to the VFS interface rather than any specific type of file system. First we have file system interface, then VFS interface. From that it is divided into local disk type 1, type 2 and type 3. Okay. So this is the diagram for virtual file system. Now, how to implement a virtual file system? For example, Linux has four object types in node, file, superblock, den tree. VFS defines set of operations on objects that that the objects that must be implemented. Every object has a pointer to a function table. Function table has addresses of routines to implement that function on that particular object. Some examples are given: to open a file, already open file, read file, write file, memory, map a file. So these are the examples for virtual file system implementation commands. That's all for today's class. Thank you and have a nice day.